So moving right along in part 2 or part B of this lecture 5 series, we're going to jump right in where we left off and continue talking about Vmax, Km, and we'll introduce a third variable, Kcat, into the discussion as well. We already talked about these a little bit, or at least Km and Vmax in the previous chunk, and we'll expand on it here. Just to remind you, there'll be one more chunk to this lecture series where we talk about inhibiting enzymes, and more importantly, we'll talk about the effects on these three variables in the presence of different enzyme inhibitors. So let's pick up right where we left off. We left off talking about Vmax and Km and the importance of each. We would like to know how efficiently an enzyme achieves catalysis, and that's really what Vmax tells us. It gives us an idea of how quickly an enzyme can go when all throttles are at 100%. And Vmax leads to Km. Km lets us understand how well enzymes bind to their substrate, which is also important to know. But most of the time, with our standard Michaelis-Menten graphs like the ones we were looking at before, it's not so easy to determine from the graph where Vmax really lies. We have to find that maximal velocity, and it's often hard to figure out or find out where that reaction velocity has stopped increasing. So if we look at this graph here, we see a constant and steady increase where we shift from first order reactions towards zero. But is this Vmax? Is that really the top of this graph? Is it going to go no higher than this? Or is it going to go a little bit higher? Or if I go way out here, is this graph going to continue to climb? And it turns out Vmax is all the way up here. This graph continues to increase for quite some time, little by little, with substrate concentration increases until it maxes out at this value and never gets any higher. I don't know about you, but I would never guess that Vmax was this high if all you showed me was this experimental data shown by the blue curve. So Vmax is important. We need to know Vmax if we're going to understand more about enzymes, but Vmax is not always clear and obvious from standard biochemical graphs. And if we aren't sure what Vmax is, we're never going to come to an accurate prediction of Km, and Km is another important value that we need to know. And why do we need to know Km? What is Km important for? I hope every single one of you said out loud, and I don't care who's around listening, that Km tells us how well that enzymes bind to substrate, and that's why we need to know Km. Is this a good substrate binder, or is this enzyme a poor substrate binder? And we can only answer that question with Km. So we need a good value for Vmax. We can get there very haphazardly with some advanced algebra using the Michaelis-Menten enzyme equation, but we don't want to do that. That's a little bit too much for us. Instead, we can take an easier, more simple approach where we transform that previous graph, that indecipherable blue curve, into a plot that is much more easily read and interpreted. And we can do that by taking the reciprocals of all the terms in the Michaelis-Menten equation. We're essentially going to turn the Michaelis-Menten equation upside down. So this is what we get when we take the reciprocal of the entire Michaelis-Menten equation. To remind you, this is the equation itself. V equals Vmax times substrate concentration over Km plus substrate concentration. And if you look closely, all we did was take the reciprocal of both sides. I'll toggle one more time so you believe it. The reciprocal of V is 1 over V, and the reciprocal of Vmax times substrate over Km plus substrate is the opposite. So this is the reciprocal of the Michaelis-Menten equation. Yippee! How does that help us? Well, using just a little bit of algebra, we can actually pull these apart. So if we remove this denominator of substrate concentration as 1 over substrate concentration, what we can essentially say is that 1 over the velocity, we keep the left side of the equation the same, is equal to Km over Vmax times 1 over substrate, right? And that's what that is. Km over Vmax times 1 over substrate would be Km over Vmax times S, plus 1 over Vmax itself. So we can separate this equation, this term, into these two terms here, and get the same result. Now if you look really closely, you'll see that this essentially is the equation of a line. The general equation of a line, as I'm sure you know, is y equals mx plus b, where b is the y-intercept, m is the slope, and x and y are individual coordinates on that line. Y equals mx plus b is the same as 1 over v equals Km over Vmax times 1 over S plus 1 over Vmax. In other words, our y coordinates are 1 over velocities, or the reciprocal of velocities. The slope of the line we'll generate is Km over Vmax. Our x coordinates are 1 over substrate concentrations, or the reciprocal of substrate concentrations. And our y-intercept is 1 over Vmax. So we have turned an indecipherable curve into a very easy to interpret line. The y-axis of our new graph will be 1 over velocity. The x-axis of our new graph will be 1 over substrate. And we'll turn this into a line with a slope that's Km over Vmax and a y-intercept that's 1 over Vmax. So we converted this into this very difficult to interpret graph into a straight line. A line is much easier to decipher from a Michaelis-Menten perspective, and we'll see why in just a moment. We call this line, or this plot on the right, a Lineweaver-Burk double reciprocal plot, or often a Lineweaver-Burk plot for short. We call it a double reciprocal plot because that is indeed what it is. It is the reciprocal of the substrate concentration graphed against the reciprocal of the velocity. So it is a double reciprocal plot because we're putting 1 over V over 1 over the concentration of S. To draw a line, as you know, all you need is a single point and the slope, or 2 points and a ruler. Also, you can just as easily use experimental data, as we did for the graph on the left, to generate either one of these graphs. Remember, these two graphs represent the same data, the same values. It's just that the graph on the right represents the reciprocal of the graph on the left. The reason why we're going through all this trouble is, unlike the Michaelis-Menten graph on the left, the Lineweaver-Burk graph allows you to very easily and unambiguously determine Vmax and Km, the values we were after. Vmax is the reciprocal of the y-intercept, and Km is the reciprocal of the x-intercept once we strip away the negative sign. We know that the y-intercept is 1 over Vmax, or the reciprocal of the maximal velocity, because that's what that is in the term. This here is the y-intercept. So in your textbook, you have this practice problem. You're given a series of different substrate concentrations that were experimentally controlled in millimolar, and you're also given the values of the velocity of the reactions that were measured at those 5 different substrate concentrations. The question then asks you to construct a Lineweaver-Burk plot and determine the values for Km and Vmax. The first step of solving this problem is calculating the reciprocals of these values. In other words, you would do 1 divided by 2.5 and get 0.4. 1 divided by 5 is 0.2. 1 divided by 10 is 0.1, and down you'd go. You would do the same here for the velocities, and do 1 divided by 0.024, and you'd get 41.7. 1 divided by 0.036, and you'd get 27.8, and down you'd go. Now, with each of these reciprocal values in hand, you would plot them on graph paper and come up with these 5 points or coordinates, using each of those starting points as your, each of these values as your coordinates for these points. Then you would draw a best fit line through those 5 points as best you can, and that is the line representing your enzymatic reaction. Remember, Vmax is the reciprocal of this value, and Km is the reciprocal of this value once you strip away the negative sign. So with those 2 values in hand, you can determine Vmax and Km. Could you do this on your own if needed? Right now, you're probably saying no, and that's understandable. You've only been exposed to it just now. But let me say, you will need to be able to do this for the Unit 1 exam. I hold each and every one of you accountable for being able to take experimental enzymatic data and use that data to generate a Lineweaver-Burk plot that you can then use to determine Vmax and Km of the enzyme in question. I've put together an online tutorial for this where I work through a problem from beginning to end for you to watch and tag along. That's on YouTube under the biochemistry review videos. I encourage you to watch that video and try to do the problem with me if you're feeling very uncomfortable with these manipulations. So we're going to a whole lot of trouble to figure out Km and Vmax. Why? Well, it's because of how important these values are for understanding the enzyme. Km is the substrate concentration when the velocity of the reaction is at half its maximal rate. Or said another way, it's the substrate concentration when the enzymes are half saturated. So that's where we get at this notion of the efficiency of enzyme substrate binding. If Km is really the substrate concentration where 50% of the enzymes are bound to substrate, then, and that's because Vmax represents when we have 100% saturation, then Km is really giving us an idea of how well enzyme wants to bind to substrate. Imagine you had two enzymes. One enzyme has a Km of 50 millimolar. That would mean you need a concentration of 50 millimolar substrate to fill half of that enzyme's active sites. The other enzyme has a Km of 15 micromolar. That would mean you need 15 micromolar of substrate in order to fill 50% of that enzyme's active sites. What we're really asking here is which enzyme binds to its substrate better, more tightly, and more efficiently. Perhaps think about this a different way. Instead of enzymes, let's think of two different guys that are hanging off a wall. One guy needs 50 feet of rope to hang on without falling. The other needs 15 feet of rope to hang on without falling. And I'm essentially asking who holds on to rope better, more tightly, and more efficiently. You would likely tell me the individual who only needs 15 feet of rope binds to that rope better, and that's why they only need 15. The reason why the first dude needs 50 feet is because he has a harder time interacting with the rope, so he needs more of it. And the same logic applies for enzymes. Enzymes with lower Kms need less substrate in order to reach 50% saturation because they bind that substrate more efficiently. Enzymes that bind substrate less efficiently and don't prefer to bind to their substrate need more substrate around in order to get to 50% saturation. That more substrate around leads to larger Km values, and larger Km values mean that we have worse enzyme substrate binding. Hopefully it makes common intuitive sense once you begin to think of it in more realistic real-world terms. Back to Vmax. Vmax is intimately related to the last variable we have yet to introduce. This is the idea of turnover number. Turnover number is symbolized as Kcat, the catalytic constant. Kcat is actually equal to the second rate constant that I showed you at the beginning of the first chunk. This is the rate constant of the enzyme substrate complex going to product. This is our turnover number, how quickly the enzyme makes product once it makes enzyme substrate complex. Kcat is the amount of substrate the enzyme can turn into product per enzyme when it is at its maximal velocity. Vmax and Kcat again are intimately related, and they go up and down together. As Vmax goes up, Kcat goes up. As Vmax goes down, Kcat goes down. So to tie all these ideas together, here's how I understand the big picture of Michaelis-Menten enzyme kinetics, and I hope it helps you tie things together as well. We go back to our overall generic equation here. Enzyme and substrate independently come together to form an enzyme-substrate complex, and then once enzyme makes transition state in that complex, it breaks down, transition state breaks down into product, and enzyme lets go. This first part, enzyme and substrate separately, coming together to create the enzyme-substrate complex, that's where Km comes into play. Km is directly related to the efficiency of substrate binding, and substrate binding is only important here in phase 1 of the reaction. Once enzyme-substrate complex is formed, what we need to happen next is the creation of product, and that's the turnover number. The amount of product we can make per unit time is our Kcat. Vmax kind of takes both of these ideas into consideration and says how much substrate do we need to get to our maximal velocity, and once there, what is our maximal velocity? So Vmax ties these ideas together by saying how much enzyme do we need to be at 100% capacity, and what is 100% capacity actually mean? How much product can we make when we're at full throttle? Some examples of where these values fall in the real world. We have here 5 different examples of common enzymes. Catalase is an enzyme that converts hydrogen peroxide into water and oxygen. It has a very, very fast turnover number, about 40 million reactions per second, which is huge. It's got a very, very good and enviable Kcat. Km is awful. Catalase hates binding to peroxide. A Km of 25 is really, really bad. Carbonic anhydrase is a good enzyme as well in terms of catalysis. Once it can create the enzyme substrate complex, it can catalyze 1 million reactions per second, but we see that it also has a fairly high Km. It doesn't really like its reactants, which are carbon dioxide and water. Acetylcholinesterase, now we're starting to get to slower Kcats, not quite as fast as we see there. We're more on the order here of 14,000 reactions per second, which is still pretty impressive to me. But we see our Kms are getting quite impressive now as well. We're below 1. We're several orders of magnitude below the values of catalase. Here is an enzyme that actually likes its substrate. Chymotrypsin, another balance between high catalysis and a fairly good enzyme substrate binding in the Km. And lysozyme, we see now we're overdoing it. Lysozyme has a pretty poor Kcat. It can only catalyze, a half a reaction per second. So you need 2 full seconds to go by before you have a catalyzed reaction. But lysozyme really likes its substrate and binds it with a very high efficiency. In fact, we can interpret this to mean that lysozyme probably likes its substrate so much it ain't too eager to convert that substrate into transition state. This is that thermodynamic pit we talked about in the last lecture series. No matter how you slice it, though, very, very amazing that we can understand the complexities of enzymatic reactions to this level of detail, kind of parsing and dissecting out the different aspects of enzymatic reactions. One last point to emphasize before we wrap up this chunk and switch gears to inhibition. Km, Vmax, and Kcat are properties of enzymes. They're characteristics of enzymes. They are constants of individual enzymes. Each enzyme can have different values for these properties, but those properties never change for each specific or individual enzyme. I think of these as the enzyme's eye color, hair color, and height. Those properties don't change. They're unique to that enzyme, but they are constant and trustworthy, and they are unchanging for that enzyme. It's kind of like enzymes are born with these values, and there's nothing we can do to change it. So to summarize what we talked about here, Lineweaver-Burk double reciprocal plots are our way to go when we need to determine reliable Kms and Vmaxes. Because we can convert those hyperbolic values into a line graph, we can more easily interpret that line graph and more easily calculate our Km and Vmax from that line. Km gives us information about enzyme substrate binding, and Kcat gives us direct information about the rate of turnover to create product. We're going to go now to enzyme inhibition. We're going to look at 3 different classes of enzyme inhibitors and look at how they affect enzymes in general, but more specifically how they affect these variables of enzymes, how Km, Vmax, and Kcat are influenced by different types of enzymes. As always, thank you so much for watching.